I want to do something quite different today. Instead of looking at a programming puzzle, we're going to look at a logic puzzle. We're going to solve with programming. So one of my friends made this logic puzzle. This website, which is mostly like a sort of horror fiction writing website. But anyway, he decided to make a logic puzzle for it. Yeah, so let's take a look. And then we'll see how to use a stat solver to solve it. So what's going on? So we're supposed to find a unique configuration of people, items, and where they're standing, right? There's like 8 positions to stand in. And there are some constraints on what you're allowed to do, right? So Sobong is supposed to be to the north, right? This position. The reality anchor and 2 breach alarms, which are 3 of the items, are supposed to be next to each other. Right, so consecutive. 3 of our people are nameless Class D personnel who we can't give any alarms. The chamber counterclockwise, so this way, of the rocket launcher cannot have any items, because apparently we're going to need to kill that person. Sobong cannot have the rocket launcher. Anyway, so there's all these clues, and supposedly they give a unique configuration, which we're actually going to verify. So how could you solve this with the computer? I'm going to tell you how to solve it with something called Z3, which is a, well, we're going to use it as a stat solver, but it's actually more powerful than that. But anyway, you can give it a bunch of like rules like this, and it will find you some solution satisfying those rules. So let's be more specific. So what I mean is that we're going to have a bunch of variables, right, which are bool, so they're true or false, and we're going to set them up and give a bunch of constraints on them in such a way that they like reflect the constraints in this problem. And then we're going to ask C3 to find the setting of those variables, right, true or false for each one, which like satisfies all the constraints, and that will be the answer. And so we're going. So how's that going to work? So right, there's 8 positions, there's 8 people, and there's 8 items. And for each one, we're going to have a pair, 1 Boolean for every like pair of bins. Right, so each of the people could be at each of the positions. So for each pair of position and person, we're going to have a Boolean, that's true if and only if that person is at that position. So that's 64 Booleans, right? Because there's sort of, a grid of people across the positions, and 8 of those things are going to be true, and 56 of them are going to be false, but there's 64 in total. And we're going to have the same thing for people across items, and also for items across positions. Sort of one of these sets is kind of redundant, right? If you know like where people are and where items are, then you know which people have which item. But it's going to be convenient for expressing the constraints. So that's a total of 64 times 3, which is, what is it? I don't know, it's a lot. 192, sure, Boolean variables. So obviously we couldn't like just check all 2 of the 192, true-false possibilities. So Z3 is doing something smarter than brute force, which is true. We are not going to go into what that is, mostly because I don't understand it myself. But anyway, that's a thing. And I think it can handle it even in a larger. It's actually for this problem, it's small enough that we could just check like 8 factorial squared permutations of people and items. But I want to show off how to use Z3 to do this, so we're going to do that. Okay, so we have these 192 variables that I talked about, right? Which is for each basically, each of these is like a tripartite graph, right? Each of these things has like a variable, you could think of as an edge to like each of the other 16 things. So we need to set up our constraints, which are going to be these clues from the problems, as well as some like logical constraints from the problem. So let me talk about those first. So we have constraints like every person can only be in one position, every position can only have one person, and so on, right? Like we said, we had 64 variables, and only 8 of them should be true for each of these sort of pairings, and we needed to set that. Right, so we have positions, people, and items, and iterable permutations just gives us all the pairs of them. So this is going to be like position in people, and position in item, and people in item. And so we have a constraint which says that for each, like say for each person, they can only be at one position, right? This little stanza means exactly one of these things has to be true. So of all of the positions, exactly one of them should be occupied. Right? Not 0, not 2, not 3, exactly 1. So that's giving us this constraint for all of the sort of 6 things, right, that I've listed here. Position can only be at one. Each person can only be at one position. Each person can only have one item. Each position can only have one person in one item. Each item can only have one person in one position. And the other constraint I'm adding here is just so it doesn't matter what order you list something in. So this person being in position 0 is the same thing as position 0 being with this person. So like Z3 is going to identify these variables by their names. So this is giving us the variable that's like the edge between x and y, and this is just saying that like this is unordered, right? The edge between x and y should be the same as the edge between y and x. So the other kind of thing that we have to say is, I mentioned that this is like redundant information, and so we should say that, right? So that's what these lines are doing. So if you have a person at a position and an item at a position, then it must be the case the person has the item. Similarly, if you have a person at a position and a person has an item, then the item has to be at that position. If you have an item at a position and a person with that item, then the person has to be at the same position. So this is sort of, I guess, enforcing the redundancy that we said, right? That these things sort of have to logically line up. Okay, and the last set of things that we have to do before we can get into the actual clues to the problem are, in the problem, there's some sort of like not distinct things. Like there's 3 people who are just class D. There's 2 alarms. There's 2 suits. But we want to check if there's a unique solution, so we need to distinguish them. And so what we're going to do is insist that in our solution, like D1 has a lower position than D2 has a lower position than D3, right? It's before it. And by the way, I'm identifying the positions as like 0, 1, 2, 3, 4, 5, 6, 7, so just clockwise around starting at north. Right, so like any permutations of the 3, of like D1, D2, D3 would be valid. So we're just saying, like, pick the one where D1 comes first, and pick the one where the suit 1 comes first. And the way that we do that is for each of the positions, in each of the smaller positions, we say, okay, if D2 is at that position, then D1 must be at one of these smaller positions, right, or across here. If D3 is at some position, D2 must be at one of the smaller positions. Suit 2 is at some position, suit 1 must be at a smaller, same thing for alarm, and same thing. There's only 6 items, so 2 people are holding nothing. So these sort of 2 nothing items also need to be disambiguated. Okay, so now we can give the actual clues. So long is supposed to be position 0. I've written them out in English along with the code. So this one's more complicated. This says that the anchor item and the 2 alarms have to be all next to each other. So the way that I decided to write that down is saying, okay, if the anchor is at some position, that gives us this is great. I see, yeah, okay. It must either be that the alarms are at the two positions before it, right? The position is like a clock mod 8, right? So plus 6 mod 8 is really minus 2, plus 7 mod 8 is minus 1. So they must either be at the two positions before it, they must be at the two surrounding positions, or they must be at the two positions after it. So if the anchor is at some position, then it must be either that the alarms, right, there's like 3 pairs of positions where the alarms could be, and it could be either that alarm 1 or alarm 2 is at each position, right? So for a given position of the anchor, there's like 6 different ways to set up the alarms near it. And so this is just saying, like, for each of those positions of the anchor, we need to set up the alarms in one of those 6 ways. Okay, so this is the sort of, I don't know, SAT translation of this English sentence. Okay, this one's easier. It just says class D people cannot get alarms. So for each of the class D people, and for each of the alarms, say that can't happen, right? So that rule must actually be false. Okay, this says there can't be anything to the counterclockwise of the rocket launcher. So like the negative ones start from the rocket launcher. So for each position, if the rocket launcher is at that position, we must either have nothing 1 or nothing 2 immediately before. So this says, so long cannot hold the rocket launcher. That's easy enough. Just so that particular Boolean is false. Okay. Class D people cannot be standing next to each other. So for each place where someone could be, and for all of the pairs of class D people, if one of them is standing at some position, the other one cannot be standing before him. And if one of them is standing at some position, the other one cannot be standing after him. Right, and this is just all pairs, so this is like 3, D1, D2, D1, D3, and D2, D3. Okay. This one says that Ramos has to be standing opposite the anchor, right? And because the whole thing is 8, opposite just means like 4 away from. So if the anchor is at some position, then Ramos must be at that position plus 4 mod 8. So that's fine. Domsky has to be in or next to the anchor. So for each position where Domsky could be, it must either be the case that the anchor is at that position, or the position after that position, or the position before that position. Ramos and Solong have to be exactly one chamber between them, right? So like here and here, or here and here. So either plus 2 or plus 6, right? Which is minus 2. So if Ramos is on some position, then Solong should either be 2 after or 2 before. 2 class D personnel will not be an item. So Z3 has this way of expressing at least, although you'll notice that there's only 2 no items, so it could also be exactly. But anyway, so we collect up all of the variables which represent a class D person getting no item. And this means like at least 2 have to be true. GE is greater than or equal to. So that's that constraint. Okay. So Dempsey going to a Domsky should go counterclockwise, or it should be shorter to go counterclockwise. So what does that mean? So like if Dempsey is here, then counterclockwise means going around this way. And so for it to be shorter to be counterclockwise, you'd have to be in one of these 3 positions, right? This one is equal, and this one is closer clockwise. So it just means he has to be in one of the 3 positions before. Okay, so if Dempsey is at some position, then Adamski must be at one of the 3 positions before that, right? This is -1, -2, -3. One of the researchers is supposed to get one of the suits, and the other suit is supposed to go to, this is just everyone else. Right. Supervisor, agent of class D. Well, everyone who's not a researcher is either a supervisor, agent of class D. So for all the people and for the suits, so we're going to add another, like exactly one constraint. By the way, EQ is for equals. So we need to collect up all of the variables that represent a researcher getting a suit. That's in G1. And then all the variables that represent someone else getting a suit. That's in G2. And we can say that exactly one thing from G1 has to be true and exactly one thing from G2 has to be true. This is an alternate way of putting it that I did before. This one isn't actually quite right because you don't know who's going to get suit 1 or suit 2. Okay, this says if the 2 people with suits should be near each other. They should have no more than 1 chamber in between them. So that means if one of the suits is here, the other suit shouldn't be here, right? It should be in one of these 4 spots. That is, for each position where suit 1 might be, suit 2 should be -2, -1, +1, and +2 away from it. So that's sort of the translation of this rule. Okay, and we're on to the final rule. So Morris does not want to be next to the researchers, who are Adamski and Dempsey. So for every position where Morris could be, we want to say the researchers are not next to him. So there's 2 researchers and 2 positions that are next to him. So collect up those 4 variables and say that they're not true. And all of them have to not be true. So that's what the and is for. So if Morris is some position, Adamski is not before him, and Dempsey is not before him, and Adamski is not after him, and Dempsey is not after him. Okay, so now we have finally written down all of our constraints in this sort of Boolean language. And now we can actually run, solve the problem. So we can ask C3, is there a solution? And if so, what is it? And then we can print out the solution. And then we can ask C3, is that the only solution? So the way that we ask it if that's the only solution is for all of the variables, like we're going to add one more rule, which is that the solution that you find is not exactly the same as the solution. Right? That is, for all of the variables, it shouldn't be that you set them to the same values, right? So this is some big, like if we found the solution A equals true, B equals false, C equals true. Imagine there's just 3 variables. We would add the condition, and right, we don't want it to give the same solution it gave before. So, and we can also have written this with an or, the Morgan's law. Okay, so anyway, just tell it, yeah, this is like telling it don't output the same solution, right? If you expand this with De Morgan's law, it says not A or B or C, right? So one of the variables must be different, or I guess this is sort of saying they can't all be the same. So we collect up all the variables and what they were set to in our first solution, and then we add the rule, okay, they can't all be the same as that, and then we check that there's no solution. Sat means satisfiable, there is a solution. Unsat means unsatisfiable, there is no solution. And then we can print out our solution. Right, it wouldn't be that helpful to just print 192 variables. We can give sort of more structured output. And so what we'll do is, for each of the positions, we'll find the person and the item that are at that position, right? That is, if that variable corresponding to the person being in that position is true, and the variable corresponding to the model being, or to the item being in that position is true, we can check that the person actually has the item. Right? That should be true because of the these conditions. Right? If the person's position in the items is at the position, the person should have the item. So we'll just double check that, and then we can print out like that person, that position with the item. Okay, so that's the whole thing. 160 lines. It might have been faster to solve it sort of by hand, but I don't know. I think it's pretty cool to be able to solve it, just by typing in the conditions. Right? We didn't actually do any solving ourselves. So let's see what it does. Okay. So in half a second, I guess, it computes for us that so long should be at the top with the alarm. Okay, that's good. That's what we said. And then D with nothing, Ramos with the rocket, Morris with the suit. So anyway, we have our solution. Right, and let's just check our conditions. So long is supposed to be north, left with 0, so that's good. The anchor and the breach alarms are supposed to be next to each other. So there's the anchor, and there's the 2 alarms. And so they're at these positions, 6, 7, and 0, which are next to each other. D cannot get any alarms. This guy has nothing in the anchor, so that's fine. There shouldn't be anything to the left of the rocket launcher. So the rocket is here, and indeed, this guy has nothing. So long should not have the rocket launcher. Yes, that's right, he has an alarm. Class D cannot be next to each other. This guy's at 1, 4, and 6. They're separated by named people. Ramos should be opposite the anchor. So here's the anchor, and here's Ramos. Adamski should be either in or next to the anchor. So here's the anchor, and here's Adamski next to it. Ramos and Sovan are supposed to be exactly 1 chamber away. So 1 is at 0, and Ramos is at 2, and 1 is the chamber in between them. 2 class D will not be given an item. This guy has nothing, and this guy has nothing. Dempsey wants to go to Adamski. He should go counterclockwise, should be shorter. So he's at 7, and counterclockwise is 2 away, and clockwise would be 1, 2, 3, 4, 5, 6 away. So, yep, that's right. One of the researchers should have a suit, and then one of the non-researchers should have a suit. So Adamski, who is a researcher, has a suit, and Morris, who is a supervisor, also has a suit. Yeah. The suit should be no more than 1 chamber between them. So 3 and 5, it's close. And Morris does not want to stand next to the researchers. So Morris is next to Ramos, who is an agent, not a researcher, and one of the class D people. So all these conditions are satisfied. And we also checked that this is the only solution. So that's what we wanted. We wanted to find the solution, and we wanted to find the only solution. I'm just curious how long it actually takes to find the solution. Okay. So only 0.02 seconds to actually solve all the constraints, I think. Assuming that it's not solving them as it's adding, which I think is the case. Yeah, so I was kind of surprised that this was so high, but I think the actual computation time is pretty low. So yeah, that's how you could solve this logic problem with Z3 by sort of expressing your problem as a bunch of Boolean variables and like relations between them. And you can also solve like all sorts of logic problems this way. Like you can solve Sudokus with something like this. You can solve I like Kukuros or a different logic puzzle that I like, where you have to write numbers in a grid and solve like this. I did a project earlier problem that way. So anyway, this was I wouldn't think you'd ever use this in a programming contest, but I think it's a cool tool that I've had occasion to use, a few times. I was just doing this recently, so I thought it was neat, and hopefully you think it's neat too. So that's it.